Hello and welcome to this lecture on electric flux and Gauss's law. I am Paras Khosla, a first year computer science undergraduate at Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. That's me on the right. Let's get started. So, electric flux, it is the measure of the number of electric field lines piercing unit perpendicular area. So, we need to be careful about this definition because we need to only consider the perpendicular area while writing flux. So we can uh, see from this example on the right that it if we were to calculate the flux from this inclined surface, we need to actually consider the area that I'm presently color coding in red. So this is the area that actually needs to be taken while writing flux. All right. So how can we actually compute this area? Well, we can make use of basic trigonometry. So let's see this. Let's analyze this triangle. Let's say this is L. This length is L, and let's say this is height H, and let's say the depth is D. All right. So if we were to write the cosine of theta, so we can say that H is L times the cosine of theta. Now, if we multiply both sides of this equality by D, we get this. And dl is nothing but A, and dh is nothing but the projected area. So we get this equality. So now if you were to write the flux, so the flux phi subscript E for electric, that will be equal to E times A cos theta. Now using vectors, we can say that this is nothing but the dot product between E and A. And why that is the case is, we can see from this triangle, this right triangle. Let me make it more clearly. So I'm not talking about magnitudes here, let's just see for direction's sake. This is the direction of E vector. Area vector is pointing like that along the outward normal, so that is A. Now we know that the angle right here, this is going to be a 90-degree angle because it's the outward normal. Well, and this we know, this is theta. So this angle by the property of triangles is going to be 90 minus theta, and since this entire angle is 90 degrees, this angle is going to be theta. So the angle between E vector and A vector is theta, so we can write it like that. Now if the field were non-uniform, we can take small patches over which the field is uniform and then integrate over the entire surface to get the flux. So it will be like this. This is just a fancy symbol for symbolizing that we are actually integrating over the entire surface. So E dot dA. All right, now we can move on to study Gauss's law. So the person on the right is Carl Friedrich Gauss, and the Gauss's law, as you can make out, is named in his honor. So this right here, it is the mathematical statement of Gauss's law, and we just in the previous slide we evaluated this integral to be the electric flux. So Gauss's law can be rewritten as the electric flux is equal to the enclosed charge divided by epsilon naught. Epsilon naught is the permittivity. So let's try to make sense of this. So let's say we have a closed surface. Uh, by the way, this is called the Gaussian surface. Let's say that the surface contains charges q1, q2, and q3, and the charges q4 and q5 lie outside it. So if we were to write the electric flux through this Gaussian surface, let's call it S. So the electric flux by Gauss's law would be the algebraic sum of the charges that are enclosed within the Gaussian surface. So in this case, it will be q1 plus q2 plus q3, this thing divided by epsilon naught. So that will be the flux. Now, the charges that are outside of the Gaussian sphere, like q4 and q5, they have no role to play in the flux. However, if we consider this integral over the surface E dot dA, they absolutely play a role in this electric field right here. This electric field is the field at that point due to all of these charges in space. So that is to be kept in mind. Now, now let's verify Gauss's law. We have not proved it, and we can only verify it at this level. So let us consider this sphere of radius small r. So its equation will be x square plus y square plus z square is equal to r square. So let's assign names to these axes, and by the right hand coordinate system rule, we must make the axis such that I cross j is equal to k cap. We said by the right hand rule. Now, if we consider a point charge to be placed at the origin and the charge is q, we can write the electric field at any point on this sphere by the Coulomb's law, which will be kq upon r square, radius square, r cap. This symbolizes the direction and it symbolizes that it is radial. Now if we were to write the electric flux, we can write phi e, that is going to be equal to integral over this entire sphere of E dot dA. This is just Gauss's law. Now we can replace kq by r square r cap dot dA. For this surface, radius is constant, so we can bring it out of the integral and we'll be left with this. Now, since r cap is in the radial direction and so is dA, because dA vector is pointing towards the outward normal, so this thing will just evaluate to kq by r square. Since the magnitude of r cap is 1 because it's a unit vector, it will just evaluate to this, right? And this thing on the right, this integral on the right, is nothing but the total surface area. So if we write it as 4 pi r square and we just plug it in and we rewrite k is equal to 1 over 4 pi epsilon naught, we can see that phi e electric flux is indeed equal to Q, which is the enclosed charge over epsilon naught. So hence we have verified Gauss's law. Let's try this problem out. The question statement is, find the flux passing through the square plate of side A given that the charge Q is placed at height A by 2 above the center of the plate. The height is 1/2 of the side of the square. I suggest you to pause and try this out on your own, assuming you've had a go at it. Now let's work through it together. So a good starting point would be to assigning axes. So let's say this is x, and let's say this is y. So by the right hand rule, this has to be z. All right, because I cross j is k cap in the right hand coordinate system. Now we can consider a small patch on this square of thickness dx cross dy. This is y, this is x. All right, and we can find the flux through this. Let me switch colors. So okay, this is the field line right at this point, and let's see how far this actually is from the origin. So let's say that distance is s. So by the Pythagorean theorem, s is nothing but square root of x square plus y square. And let's make use of this triangle, which also is a which is a right triangle. Make use of the Pythagorean theorem to write this length L, which will be used in writing the electric field. So L is the square root of s square plus h square, this height, which is, well, a by 2, half of the side of the square. So square root of x square plus y square plus a by 2 quantity square. Now to write the flux through this small patch of area dA, or we may call dA as dx times dy. Alright, so the flux through this small patch is going to be E dA times the cosine of this angle. Let's say this is theta. Let me switch to a different color. Say this angle is theta. Cosine of theta. Cosine of theta. Alright. So E we can write using Coulomb's law, K Q over L square times dx dy times the cosine of theta, which is going to be h over L. H is a by 2 and over L. So we can simplify this to k q a upon 2 L cube. Well, to write L cube, we can write x square plus y square plus a square by 4 raised to the 3 by 2 power and times dx dy. When we integrate both sides of this equation twice within the proper bounds of integration, we'll get the flux, and those bounds will be from minus a by 2 to plus a by 2 for x as well as for y. Now this is a very daunting and a very tedious task to do, so I'll present a wonderful method in the next slide, which is sort of a trick. So we can complete this cube entirely and then make use of Gauss's law. So the flux through this entire cube is going to be the enclosed charge, which is, well, Q divided by epsilon naught. Now, six faces. So there's six faces to a cube, and we wish to find the flux through a single face. So let's say this bottom one right here. You wish to find the flux through this. So by this argument of symmetry, since all of these faces are identical in both orientation and in size, the flux through each of them must be the same. So 6 times the flux through a single face, because there's 6 of them, should be equal to the flux through the entire cube, which is equal to Q by epsilon naught. So we can now write down the answer. Phi through a single face is going to be 1/6 Q over epsilon naught. So that's the answer. So I hope you enjoyed this lecture. Thank you so much for patiently listening to it.